We hate it.
Okay. So,
Trolling. We're trolling.
so here's the program that you've got. And so basically, at the beginning, you're going to look at what's going to happen when you have a positive source that's generating this field. And then you're going to have a negative electron that you're going to put in there, and you're going to see what's going to happen. Okay? So, one of the things that you're going to look at is that how you're going to calculate this value of the electric field. And this is what we went over yesterday. There's kind of three different ways you can calculate that electric field. KQ over R squared, it's V over D. Those are the two that you're going to use most often. So over on page 2, okay, on number 15, everybody's favorite thing, let's look at it from a units perspective. So you're going to prove, just kind of like what I did yesterday, that if you find that electric field based upon the two different ways of KQ over R squared and V over D, that you're going to get the same units. Now, the whole key to this is that hint that I gave you that volts are joules per coulomb. So one of the things that you need to begin to get straight in your field is that an electric field is measured in newtons per coulomb. So it's force per unit of charge. The other way, if you look at E in terms of voltage, voltage is joules per coulomb. Okay, so voltage by itself is measured energy per unit of charge. Electric field is force per unit of charge. Okay, they're two distinct things. They're kind of related, but they're really not. So when you get to part 2, okay, you're going to clear everything out and you're just going to start all over again. So the whole point of part 2 is that I want you to look at a comparison of what happens when you have two positively charged particles in terms of the electric field and two positively charged particles when you have the voltage. Okay? They're kind of opposite. So if you have two positive charges, you can look at an electric field as being like a vector quantity. So in the middle, that electric field is going to cancel each other out. Because remember, when you're defining the direction of an electric field, it's defined by the direction a positive test charge would move if you put it in the presence of that field. So what you should see, because of the fact that your electric field is KQ over R squared, as that electric field gets further and further, as you look at the strength of that electric field, as you get further and further and further, that electric field becomes weaker and weaker and weaker. Very similar to what happens if you have the Earth, okay? And as you get further and further and further from the Earth, the gravitational field becomes weaker and weaker and weaker. Same thing is true of a light. As you get further and further and further from a light, that intensity decreases as a function of R squared. It's an inverse square law. We've studied any number of these, okay? So what can happen is, if you're in the middle, the electric field basically drops to 0 because of the fact that you have two repulsion forces, that those electric fields, remember, because it's force per unit of charge. So one's pushing it this way, the other one's pushing it this way. Now, if you have a positive and a positive, that can happen. If you have a negative and a negative, then it's like a mutual tug of war. So instead of being squished, okay, now it's going to be pulled if you put a positive test charge in the middle. So conceptually, that's easier to get. When you get into the voltage, okay, so what you need to realize on the voltage is that your voltage is, this is what I gave you yesterday, KQ1 over R plus Q2 over R plus da-da-da, however many that you have, okay? So voltages are based upon charges. So if you have two positive charges, okay, in this situation, then there's no way your voltage in the middle can drop to 0 because you're adding two positive values together.
Okay.
But your electric field can go to 0 when you have two positive charges because your electric field is going to cancel out. But if you look at this in terms of voltage, in terms of like, this is how this plays out. Imagine that you've got a positive test charge a long, long way away. And you're going to push that positive test charge so that it exists in between those two positive charges. So it's like you're pushing this thing up two kind of mountains. So when you push that thing up between those two mountains, that's going to store a tremendous amount of energy Because remember, voltage is joules per coulomb. Electric fields are force per coulomb. So when you have two positive charges or two negative charges, so what happens, like I said, we'll spend a lot of time talking about this from an energy perspective. If you have two negative charges, instead of pushing it, remember that negative charge would, if you put a positive charge in between two negative values, it would want to go in that direction because it's going to be attracted to it. So if that's the case, you kind of actually have to keep it from going in that direction. So it's like you're trying to keep a ball from rolling downhill if you have two negative charges. So that's why that's going to be a negative value. Now, if you have a positive and a negative charge, okay, then if you're right in the middle, it's like you're at the bottom of the valley of the potential energy well. So if you have a positive and negative, then that positive test charge is going to kind of pull it in terms of energy. It's not going to have really much energy to go to either side because you're at the bottom of this energy well. Okay? So if you have two positives or two negatives, your electric field can cancel out. But you're going to have voltage. If you have a positive and a negative, your electric field can't cancel out because it's going to be pushed and pulled, but your voltage will go to zero. So that's one of the key things that I want you to get out of part 2. Okay? That's the whole reason that I wrote part 2 in terms of what I want you to get out of that section. Now, when you get over to part 3, because then I'm basically going to turn you loose to a certain extent and let you work for a while. So what's happening on part 3, you're going to double stack two positive charges at an intersection, kind of on the right side of the screen. So you're going to come in here and you're going to put two positive charges, one there, and then put that at an intersection, okay, which is tough to do with sliding finger. And then you're going to put another one on top of that, and then you're going to put a negatively charged particle 1 meter away, something like that. So what you want to do is you want to calculate the distance, if it exists, at which the electric field will drop to 0. Okay? So just think this through. So if I put a positive test charge here, don't worry about these double stacked positive charges over here. I'm going to put a positive test charge here. What's it going to feel relative to the negative charge?
Attraction.
It's going to feel attraction, right? What's it going to feel from the two double stacked positive charges?
Strong repulsion.
Strong repulsion, but it's going to be a long way away. So basically, what I want is for that distance to be where the attractive electric field is going to feel this way, is going to equal to the repulsive force it's going to feel from the double stacked values there. So because you're talking about these electric fields, okay, so you've got that double stacked positive. 1 meter away, you've got a negative, okay? So that's going to be 1 meter. So I know this point exists somewhere out here, right? Now, I know it can't exist on the right side. Why do I know it can't ever go to 0 on the right side? Yeah, because of the fact that this is the bigger positive charge, okay? And this is the smaller negative charge. So I know it can't go to 0 over here. I know it has to be somewhere out here on the left side. Now, so here's the deal. So basically, these two electric fields, one from the negative and one from dose positives, okay? It's the physics game, dose positives. They have to equal each other, right? So you're going to have KQ over R squared, right? Okay, so this is going to be this distance R. That has to equal K times, now I've got two positive charges stacked there, right? So that's going to be 2Q. But here's the deal. How are you going to express the distance from those two double stacked positive charges out to that point? What'd you say, Peyton?
Is it 2R squared?
Nope.
R plus 1 squared? Yes, that's how I did it.
1 meter plus R, right? And then you're going to square root of that. Set the two equal, do some algebra, okay? And maybe even, dare I say, a quadratic. I'm just saying, okay? Now,
But
then below, so that's going to get you going with that. So then on number 8, you're going to go through and you're going to plot the equal potential lines. You don't have to draw a whole lot of them, okay? But notice that I want you to draw 2 things on this diagram, okay? And take your time. This isn't just a random sketch. So in the space below, sketch the equal potential curves. Again, you don't have to do like 20 of them, okay? Maybe 4 or 5 around each one. And then also draw in some of the field lines. On those field lines, what I'm going to look for on those field line drawings are specifically which direction they are pointing, okay? So just don't draw random lines and think, oh, there's my field lines. Your field lines have to have arrows pointing on them, okay? So, all right, so that should probably take you a while to get through all of that. So go be free. So, you need to stop that.